Hello everyone, welcome to this problem solving video. In this video we are going to solve problem 53 of chapter 23 from Halil-Resnick-Walker. This problem is particularly interesting because it deals with a non-uniform distribution of charge. Let's start solving the problem. The volume charge density of a solid non-conducting sphere of radius r equals 5.60 centimeter, that is say r equals 5.60 into 10 to the power minus 2 meter, varies with radial distance r, small r. Well, this is interesting because this is solid non-conducting sphere, and the volume charge density actually varies with radial distance small r, and this variation is given by rho equals 14.1 picocoulomb per meter cubed times small r by big R. So it varies basically linearly. If small r is 0, then the density is 0. That is, you are at the center of your sphere. The green sphere is the actual sphere, the solid non-conducting sphere, and the blue sphere is our Gaussian sphere. The radius of the Gaussian sphere can be different than the actual sphere. Here, if the radius is say exactly equal to Gaussian sphere, then the Gaussian sphere actually encloses the solid sphere. Now question A asks for the sphere's total charge. Well, how can we find it? Well, this is A. So if the charge density was uniform, then it was fairly straight. It would have been fairly straightforward. Q enclosed equals rho times volume of the sphere. It's that simple. But this is not the case because the density rho is not uniform. It increases as the radial distance small r from the center of this sphere increases. So we have to do the integration. Well, this is very simple basically. dv, the integration. We have to do this volume integration, and if you do that, we find the enclosed charge. Okay, so let's do this for question A to find the total charge inside the sphere. Q enclosed when small r equals big R. This is the case when we are considering the entire sphere. So this is equal to integration rho, which is 14.1 times 10 to the power minus 12 coulomb per meter cube. This is a constant r over r, and dv. Well, this is volume, so big V. Now, to find this volume element, we need to consider the spherical coordinate system. I will leave a note after this video. You'll find a PDF here, and the spherical coordinate system will give us dv equals r squared sine theta d theta d phi dr. It may looks a little scary, but in our case it basically reduces to something like 4 pi r squared dr. That's because we only have radial dependence. Okay, I have explained it. You'll have the PDF, so you can look there. So ultimately we have this. Okay, so if we use that here, then 4 pi is basically a constant. So 14.1 times 10 to the power minus 12, 4 pi, and this big R, which is actually a constant because the radius of the actual sphere is is not a variable. So r dv becomes r squared dr, and the limit of this integration is r equals 0 to r equals big R, because we're considering the whole sphere. Okay, so if we do this integration, then we will find the enclosed charge. 14.1 times 10 to the power minus 12, 4 pi divided by r, and here it is r cubed dr integration 14.1 times 10 to the power minus 12 4 pi divided by r to the power 4 divided by 4, and the limit is 0 to big R. So probably you guessed it, we'll just have big R to the power 4. You need to be familiar with this kind of integration. If you recall, integration of x dx or x to the power n dx is basically x to the power n plus 1 divided by n plus 1 plus c. You will not need this c if this is a like definite integral with some limit. That is the case in here. 4 pi divided by r power 4 divided by 4, so this 4 cancels out. r to the power 4 divided by r is basically just r cube, so 14.1 times 10 to the power minus 12 times pi times r cubed. So that is the enclosed charge by the total sphere. Okay, so you just need to do this integration, that's all. Now what is the next question? Let's look at that. What is the field magnitude E at small r equals 0, small r equals r by 2, small r equals big R? So since we have calculated the enclosed charge for this case, r equals big R, let us first evaluate electric field magnitude for this small r equals big R, that is question D. It will be easier for us. So question D, well, if you remember, the Gauss's law in our symmetric case becomes basically E, the electric field magnitude, times the area of the Gaussian surface equals Q enclosed divided by epsilon naught. Okay, so E is the field magnitude, A is the area of the Gaussian surface. Here it is 4 pi big R squared, because recall that this is r equals r case, small r equals big R. And the enclosed charge, we have just calculated it, just 14.1 times 10 to the power minus 12 times pi times r cubed divided by epsilon. Now notice that this r squared and r cubed basically leaves us with just r. So E equals, this pi cancels out, so we have 4 epsilon naught 14.1 times 10 to the power minus 12, pi cancels out, just r. So that's the expression. You just put the value of r, you find the electric field. Okay, now let's calculate C then B. There is a reason that I want to calculate C first. So in C, we need to calculate enclosed charge at r equals r by 2 first. So what was our expression? It was basically like this: 14.1 times 10 to the power minus 12, 4 pi over r, and the limit of the integration will be r equals 0 to small r equals r by 2. So let me just copy it from here, and it's basically very simple, just the limit will be different. So this will be r over 2. So in the same way, you can find this, you can evaluate this integral. We'll have 14.1 times 10 to the power minus 12, 4 pi over r to the power 4 divided by 4, 0 to r by 2, and then 14.1 times 10 to the power minus 12, 4 pi divided by r to the power 4 divided by 4 times 2 to the power 4, because of this r by 2 here, and 2 to the power 4 is basically 16. So 14.1 times 10 to the power minus 12 pi r cubed divided by 16. So if you well, we have calculated this before. uh, 14.1 times 10 to the power minus 12 pi r cube is the total enclosed charge. Here we have the exactly same expression, but this is divided by 16. So 1/16th of charge is enclosed by radius small r equals r by 2. That is, if your Gaussian surface, the radius of the Gaussian surface is half the radius of the actual sphere, and the charge distribution is given by this relation, then that half sphere will contain 1/16th of the total charge. Now, what is the electric field? Again, this is very simple. So E times A equals Q enclosed for R equals R by 2 divided by epsilon naught, and this area A now is 4 pi R by 2 whole squared. Area of the Gaussian surface, not the actual sphere. And here Q enclosed is nothing but QNC small r equals big R divided by 16. So 16 epsilon. So what next? It's just 4 pi r squared divided by 4 equals 16 epsilon naught 14.1 times 10 to the power minus 12 pi r cubed. So 4 cancels out, pi is here, so r square cancels out. So E is equal to 16 epsilon naught 14.1 times 10 to the power minus 12 times r, because pi cancels out, this 4 cancels out, it just left with this expression. It is for r equals r by 2. Now lastly, what will be the electric field at r equals 0? Well, probably you can guess it, because this is question B, and if small r equals 0, then the net enclosed charge at r equals 0 will be 0, because there is nothing to enclose. Therefore, electric field will be 0. So at small r equals 0, your electric field is basically 0. And lastly, we have this E to graph the electric field magnitude versus R. This is very important because you will have a total overview of how the electric field changes when the charge density is given by this relation. Charge density is linearly increasing with the radial distance. So to plot it, E of R vs R. Let me just draw an axis here. This is x-axis, this is y-axis, and this is the radius of the actual sphere R. So instead of x-axis, let me label it as small r, and instead of y-axis, let me label it as E of R, as a function of R. Okay. So at this point, at r equals r, we know the electric field will be maximum from our lecture videos, and if the radius small r is greater than big R, then the electric field will follow 1 over r squared law, 1 by r squared inverse squared law basically. So just like this. And if small r is less than this big R, electric field in this case will be like this. It will increase slowly, not linearly. If the charge distribution was uniform, then we would have a linear relationship when small r equals less than big R. But in this case, this is not the situation here. Charge density is linear, and that's why our charge will increase non-linearly, and therefore we'll have this shape. Let me say a few words on spherical coordinate system. So I have drawn a diagram here, and we have this x and y and z axis as labeled using the right hand rule. This vector r is the actual vector, the distance from the center of our coordinate system, and this vector r, although I haven't used the vector sign, actually makes an angle of phi with z axis, and the vector r, the projection of vector r onto the xy plane is r prime, small r prime. I've written it here, and this small r prime makes an angle of theta with the x-axis. If this is the case, then we find that the x, y, and z component of this vector r is basically given by this relation. Z component is r cosine phi, x component is r sine phi cosine theta, y component is r sine phi sine theta. And the lower and upper limits for this variable r, theta, and phi is given here, as you can see. So we basically needed to calculate the volume element, which is dv equals dx times dy times dz. And if you do some calculations, you end up with these relations: r squared sine theta, d theta, d phi, dr. But since we didn't have radial dependence, with theta or phi dependence in our problem, we only had radial dependence. So that's why we can integrate them out, the theta and phi dependence. And if we do this integration, we find that the volume element dv corresponds to 4 pi r squared dr. And that's how you find the volume element using a spherical coordinate system.